I will begin by summarizing, perhaps from a different perspective, what was explained on the previous lecture. So this was about the canonical operator. So the main geometric object is Lagrangian manifold. So we have, as usual, the phase space with coordinates x, x1, xn, and the dual momenta p, p1, pn. And in this phase space, R to n x p, we have some Lagrangian manifold lambda n Lagrangian manifold, and recall that by saying that this is a Lagrangian manifold, I mean two things. First of all, the restriction, the pullback of the symplectic form is 0, where I is the embedding of lambda n into R to n. And second, the dimension of lambda n is equal, strange it may seem, n. So the first condition admits the manifold to have any dimension between 0 and n. In general, such manifolds with the first condition alone are known as isotropic manifolds, but an isotropic manifold of maximal dimension n is called a Lagrangian manifold. So this is the first and the main geometric object which underlies the construction of the canonical operator. And the second object, not maybe so important, but still is
dx
omega 2 is the standard symplectic form dp dx, the sum from j1 to n, dpj wedge dxj, the standard symplectic form, symplectic structure on R to n. So, and the pullback of this form under the embedding is 0. Well, okay, and this is the first geometric object, and the second geometric object is what is called a measure. This is the first. And the second is a measure. I will write it as d sigma. And by saying a measure in the theory of canonical operator, one doesn't mean just any perhaps very pathological measure, but just a smooth volume form. On lambda n. Well, of course, there are some subtle questions, such as what does one do when lambda n is not orientable? Then one takes an odd form, but I will not go into detail. So let's assume that lambda n is as good as possible, in particular orientable, so there exists a volume form on it. And so this.
Just for students, as far as I understand, lambda n, for the Helmholtz equation, lambda n is just affiliated by the trajectories of the Hamiltonian system corresponding to the canal.
Yeah, exactly. Exactly. Well, okay. So this is, we have a pair lambda n and this volume form d sigma on it, and having this pair, we construct a canonical operator, and the canonical operator It is an operator which acts on, say, compactly supported functions on lambda n, and takes these functions to functions, well, I will write just vaguely, functions of two arguments, x and h. H is the small parameter, positive, and this, I do not specify this space here, functions which have some nice properties. I will maybe specify later, but now it is not so important. Important thing is that we take functions on our Lagrangian manifold and obtain functions on the physical space which depend on the small parameter h. The typical formula for such a function is as follows. Well, let me write it here. Typical formula for a function which lies here, which is in the range of k. So psi of x h is equal to I over 2 pi h to the power of m over 2 integral phi of x theta a of x theta d theta, where theta is in Rm. These are parameters over which we integrate. I do not exclude the case where m is 0, then there is no integral, in fact, and we have just a WKB function. Well, such an integral, here we have the phase function, and here we have amplitude. Phase function, I assume it is real. And now I will explain the relation between these objects and our manifold and the canonical operator itself. So maybe at this point I would switch the boards. Well, okay, so the integral is over d theta, or that is over Rm. Well, so no. This is, so far is just a parametric integral, and now I will explain what is the relation between the properties of the phase function or whatever and our manifold lambda n and the canonical operator. So this is a local representation of the canonical operator, in fact, but I now will explain in more detail. So first, phi of x theta is assumed to be real, valued, and smooth. And a of x theta is assumed, let me say, c naught infinity, just as is customary in the theory of the canonical operator. When we speak of general matters, it is very convenient to assume that the amplitude is compactly supported. Then all integrals converge and everything is good. But when you speak about specific applications, then you may well use non-compactly supported amplitudes so long as the integrals you use still converge and have nice properties. So in general theory, it is not so important. So let me assume it is compactly supported. And so this phi phase function is non-degenerate. Non-degenerate. Well, what does that mean? By definition, this means the following, that the differentials of these functions, the derivatives of phi with respect to the theta variables, they are linearly independent on the set which is denoted by C phi. This is the set of points x theta, where is 0. The set of stationary points of this integral. The set of stationary points of this integral. So, okay, so if we have a non-degenerate phase function, then we can immediately construct a Lagrangian manifold. So let us take this C phi. If the phase function is non-degenerate, then this C phi is a smooth manifold by the implicit function theorem. And we can construct a mapping, let me take denoted by J, from C phi to R to N xp, which acts as follows. It takes any point x theta to the point x d phi over dx of x theta. Of course, it is defined for all x and theta, but I only restrict this to C phi. And so it can be proved that the image of this mapping is a smooth manifold. Let me denote this J of C phi is lambda phi. And this is a Lagrangian manifold, necessarily. This is a Lagrangian manifold. So, and if we have our original manifold lambda n, and if our lambda phi is a subset of lambda n, then such integrals as in here can be used to represent the canonical operator locally. That is for functions on lambda n whose support is in lambda phi. And how do we do that? So we write the following k phi.
Lambda phi is just one of the possible Lagrangian manifolds, right?
Yes. So the picture is as follows. Here we have our Lagrangian manifold lambda, and here we have a subset lambda phi, a subset of it. So for functions a in C not infinity of lambda phi, I can define the canonical operator via this oscillating integral. And so the formula is as follows. This is, well, let me write this I of phi a, where I of phi a is just this phase integral for short, not to write again the integral, where the restriction of a to C phi is equal to J star of phi times the square root of some Jacobian f, which I don't bother to write here, which can be written in terms of the measure and the mapping J. So if two functions have the same restriction to C phi, then their difference gives O of h in this integral. So this condition defines this I of phi a modulo O of h. So with this formula defines the canonical operator locally for functions with support in lambda phi. Well, but so if we have two different, say lambda phi 1 here, and we have another representation, then they need not coincide. The point is that the square root is not unique. We have two possible choices for the square root on a connected, simply connected set. And so to make these functions coincide, we must make some special choices of the arguments of this function f in each of the charts thus constructed. When we finally cover all of our manifold with these Lagrangian charts, then the condition that we can choose the arguments of these functions f in a consistent way throughout the manifold gives rise to the quantization conditions, Bohr-Sommerfeld-Markov quantization conditions. If you deal with, say, eigenvalue problem, then this condition gives the rule for choice of numbers which serve as asymptotic eigenvalues. Well, okay, I will not dwell on all this. I have told a little more in the previous lecture, but so these are the most general expressions for the canonical operator, and being the most general, they are useless for efficient computations because although there is a theorem, general theorem saying that if you are given a Lagrangian manifold, then in a neighborhood of any point of it, you can represent it by some non-degenerate phase function phi. Of course, existence theorems of this sort are of little value when you need to efficiently compute something. In the previous lecture, I explained how to choose this function in efficient way. The construction was briefly as follows. If you define your Lagrangian manifold lambda n locally as x is x of alpha, p is p of alpha, so you have some parametric description of your Lagrangian manifold, and you usually do have such description in specific problems, and this description is usually very natural because you can always take the natural coordinates alpha stemming from the
You want now to have global coordinates, right?
I want the good coordinates in which my Lagrangian manifold is described as simply as possible. For example, if you deal with some problem where there is radial symmetry, then possibly this coordinates alpha will somehow include the position vector and the polar angle or something like that.
Natural coordinates.
Natural.
At the same time, you want some globality, right?
This is not necessary because this representation is local, but of course, if you take natural coordinates, they tend to be more or less global. In examples which you consider the Bessel function, we had almost global coordinates. One of coordinates was the angle modulo 2 pi, but nevertheless, it was a single coordinate system in a sense on the entire manifold. Anyway, even if you cannot use a single coordinate system, you usually end up with 2 or 3 maybe in specific problems.
Okay,
But mostly global, yes, okay. And mostly global. And then you take the universal phase function phi tilde of x alpha is equal to tau of alpha plus x minus x of alpha. This is the universal phase function, where tau is the action on the manifold. The tau is p dx. Well, and then you can split the coordinates alpha into 2 groups, depending on the rank of the projection, and express one of the group via the other in x, and you get some function phi of x, say alpha prime is phi of x alpha prime, where the second group of coordinates is expressed via the first two, via some equation which I have written on the previous lecture. I will not reproduce it here. But we have seen that this leads to very natural formulas for the canonical operator, and these very abstract...
Absolutely no trajectories of any Hamiltonian system.
No. Not at all. The canonical operator, as such, is independent of any Hamiltonian system. Of course, when you solve some problem, then Lagrangian manifolds arise from Hamiltonian systems. They are, say, Liouville tori associated with some Hamiltonian or something else. But if you just speak of oscillating functions, you can construct canonical operator, not speaking of any Hamiltonians at all. You have a Lagrangian manifold, you have a measure on it, this is enough. In specific problems, Lagrangian manifold turns out to lie on the level surface of the Hamiltonian, and the measure turns out to be invariant with respect to the Hamiltonian vector field, of course. But these are additional considerations which help you solve the problem, not to construct the canonical operator. It has been constructed already.
Okay.
Well,
What the evolution of Fourier transform do? Where it comes from?
of course.
Or you will not explain?
Yeah, a special case of these oscillating integrals is Fourier transform. So you can write, say, something like that, I over 2ph to the power of n. I get the something like that. This is the specific case of this oscillating integral. Then the Lagrangian manifold is given by the equation x plus ds tilde over dp is 0. So this is the case. And if you cannot express your Lagrangian manifold in such a way, you can always split the coordinates into two groups. In one group you make the transform, the Fourier transform, and in the other you don't. This was the original construction by Maslov, in fact. But this construction is not natural because splitting the coordinates in these two groups usually has nothing to do with the problem you solve. So you end up with many charts and very awkward formulas involving some partition of unity and all that stuff. So while taking natural coordinates, you obtain much fewer coordinate charts. And so if you are lucky, you can express the canonical operator with a single integral, with a single oscillating integral. Well, that was basically what I explained in the previous lecture. I just reproduced the main points of it to make it clearer, maybe. Well, but still, this is, of course, very efficient, except for one point. If you have your canonical operator and the Lagrangian manifold is not projected on the onto the x-plane, then you inevitably have integrals. And so this, as written here, m-fold integrals. And the number m is the deficiency of the projection rank. If the manifold is projected diffeomorphically onto the x-plane, you can take m equal to 0. You have no integrals at all. You have WKB solution. If, on the other hand, the rank of the projection is less than n, and the deficiency is m, then you have m-fold integral, and not just any integral, but rapidly oscillating integral. So, of course, if you deal with supercomputers, this maybe is not a big problem. But if you do not have these supercomputers and you wish to solve your problem taking some much more moderate computing means, then there is a problem. You possibly can handle it when m is 1, but when m is greater than 1, then you are facing a problem.
Just a small question. And actually, when you write this phi tilde of alpha, then you construct the canonical operator roughly by the formula written above.
Yes. First
theta is just replaced by alpha, right?
Yes, exactly. Here, theta is alpha prime. So I first express superfluous variables via alpha and prime, and then just I use this integral with this. Theta is alpha prime. Okay, so nevertheless I have these integrals, and so it is not clear completely what to do. However, it is at the very beginning on quantum mechanics that people have noticed that they can do something. For example, if you deal with an ordinary differential equation, and this equation has a simple turning point, so then the Lagrangian manifold, let me, I hope this doesn't, then if you have a simple turning point, then the Lagrangian manifold, one-dimensional case, locally looks something like that. Here is this turning point, x naught. And so we have here the dropping rank of the projection, and the manifold looks like that. It closely resembles a parabola. And if it is the parabola, in fact, then we obtain the Airy equation. And the solution is expressed via the Airy function. So the idea was as follows. The original idea was as follows. Let's assume that we are close enough to this point. Then we possibly can drop all terms of the Taylor series of this representing this manifold, except
Maslow's idea, right?
no. This this was I guess it's called the Langer method.
Okay.
It is very early. This was just opposite to the Maslow's idea, because the Maslow's idea was, you see, this method works only in specific cases, and the Maslow's method works always. But nevertheless, the idea was as follows. Let us think, if we are very close to the point x naught, then this curve is nothing else than approximately parabola, and our psi function, our function represented by the canonical operator, even though there was no canonical operator at the time, the solution of our equation is very close to the Airy function. Well, and this worked, and so you have three zones here. You have WKB, here you have WKB, here you have Airy function, and then you paste them together and obtain the phase factor needed to proceed from up to down, and then you, if you have, say, turning point somewhere there, then you also obtain a phase factor here, and all added up, they give the correction in the Boltzmann-effect quantization rule, which was later called the Maslov index and generalized to the n-dimensional case. Well, this is of course good, but the drawback is, of course, that the size of this neighborhood depends on the small parameter h. As h tends to 0, the neighborhood shrinks to the turning point, and so it is not convenient to write the asymptotics this way, although the quantization condition is, of course, correct. Well, later there was another trend, and it is explained in very much detail in the book by Slavyanov. Well, and the trend was as follows. Let us make a change of variables in the neighborhood of this point, so that the equation, at least in the principal terms, becomes the Airy equation. Then, of course, we get the solution in the form of Airy function in some finite neighborhood, whose size is independent of the small parameter. This works pretty good with ordinary differential equations, as shown in Slavyanov's book about this. But this approach too has...
In Federico's also, actually.
Sorry?
In Federico's book too also.
Yeah, and Federico's book also, yes. In my opinion, Slavian's book is more detailed on specifically that subject. Well, but this approach also has a drawback. The drawback is that it is completely unclear how to generalize this to partial differential equations. And why it is difficult to generalize this to partial differential equations. The reason is that we ask too much. The approach is to reduce the equation in the neighborhood of this point, say, to the area equation. But it is clearly an overkill, because the solution, as we know, is given by the canonical operator on this Lagrangian manifold. So there is no need to transform the entire equation to...
Just, sorry, I have many associations with other problems. But what about boundary layer methods? They get the vary functions also.
Yeah, sure, this is another... Of course, it is...
The same way. I mean, the final result is...
Yes, sure, of course. Sorry? Yes, sure. But as far as I know, this is mainly done for parabolic equations or something like
local, very local.
Yeah, very local. So I don't. At no point in my talk I intend to tell that the method I explain is the only method to solve the problem. There are many different methods, of course. But
very important advantage is that this method is very general.
Yes, sure. And I explained why this the attempt to reduce the equation itself to the form of the area equation is an overkill. Our solution, asymptotic solution, uses only the Lagrangian manifold. So in fact, we do not need to transform the equation to the area equation. It is pretty sufficient to transform the manifold alone to the form which to the manifold which gives the area function. So I do not need to try to find a diffeomorphism which transforms my equation to the area equation. I must find the diffeomorphism which, with the appropriate transformation applied to the p variables, or in the case of one-dimensional p variable, reduces my manifold to a parabola. And then I will be done, almost. I will explain.
It's sort of generalization of this idea of taking, of studying integrals with two merging.
Yes. In fact, this is exactly it is exactly this idea. It hardly can tell that this idea is very new. It is given in Federiuk's book. The difference is that we work equally well with many dimensions, but in one-dimensional case, this is in Federiuk's book. In the case of many dimensions, this is in the book by Berry and Holes. Well, but strangely enough, there is a very long section in this book by Berry and Holes concerning integrals with generating stationary points, including multidimensional ones. But this book, there is one word which is not anywhere in this book. This word is Lagrangian manifold. So this exposition is completely ungeometric. And this is the drawback, even though they have some formulas, of course, and I will discuss this later on. Okay, so I'm...
Which book you mentioned are geometrical?
Well, this is some kind of, I cannot give the exact reference now. This is some kind of textbook on special functions published by National Institute of Standards in the USA. And this chapter about integrals with coalescing, merging singular points was written by Berry and Holes.
Very and false.
Да.
Sherlock Holmes.
W. Very and holes. Well, okay, so if anybody is interested, I can look up this reference. I, of course, have it, and I just doesn't come in mind. Well, okay. So let me now explain how things can be done in this case. Well, so assume you have a canonical operator. So you have k phi of x h. And let me say this on the Lagrangian manifold lambda. Canonical operator on the Lagrangian manifold lambda applied to some function phi, and we take a function of xh. Let us make a change of variable. X is x of y. Then this is equal to k on some different Lagrangian manifold to phi of x of y h times the square root of the Jacobian, where lambda small no, lambda tilde and lambda are related by.
But the Jacobian is inside the operator, right?
No, outside the operator. Well, where the manifolds lambda tilde and lambda are related by this change of variables, accompanied by the usual change of variables, linear change of variables in the momentum space. So this is very good formula. So, and this Jacobian is just due to the fact that the canonical operator gives, in quantum mechanical problems, the psi function. And for the psi function, we know that it is the probability density. So this is just the law of transformation for densities. When for square root of densities, we proceed from one coordinate system to another. Well, okay, this formula is very good. So if we have this Lagrangian manifold, something like that, in the x coordinates, let us transform it to the parabola. X is like that. Well, and then here you get the area function. And so this formula permits you to return the original variables. But of course there is a catch, because you get the area function when phi is 1. And if phi is not 1, then you must do something else. But this is, in fact, not a very big problem in the one-dimensional case. So you get your answer. And to make things maybe more interesting, I will explain how one can do this in the one-dimensional case without resorting to any rocket science, so to say. Well, so assume you have some Lagrangian manifold of this sort with a simple focal point here. With a simple focal point. I wish to write the canonical operator on this manifold without any integrals. So the first thing I do, I look at this manifold and I see that it is not symmetric with respect to the x-axis. So the first thing I do, I multiply my canonical operator by some exponential, so that the result is that my manifold will be symmetric. This is very, very easy to do. If I have S1 of x, S2 of x here, then S0 is, I take 1/2 of S1 plus S2. This will be incidentally a smooth function everywhere, including this point. Well, and if we single out this factor with this S0, then the resulting manifold will be symmetric. So, isolating this factor, I can assume that my manifold is symmetric. So, it suffices to consider the case of symmetric manifold, something like that. I try to draw it symmetric, but I don't succeed maybe very exactly. So, here we have some function S1 of x minus, well, S of x and minus S of x. Here it is 0. Well, so anywhere away from this focal point, my canonical operator has the form S of x, phi of x, divided by square root of dx over d alpha, plus S of x, phi, well, tilde of x, well, where here I have phi of x is my function, here phi tilde of x. Here is my expression for the canonical operator. It is very
Contributions of two rays, right?
these are two WKB contributions from these two branches. Well, okay. So what do I do? This representation is good everywhere except for this point. In this point, the functions S become singular, the derivatives of them become singular, and the Jacobian is 0. So this representation fails. However, note that the Airy function has the following representation asymptotically. Well, maybe I should write some other variable t. Plus lower order terms, and accordingly the derivatives has sign and some factors, and plus lower order terms. Okay, so if I multiply this by I and add to this with appropriate coefficients, I obtain a function I denoted by E of t, E of, well, okay, I noted by E of t, which is equal to e to the power plus lower order terms. And so let me make the change of variables here, so that here I have that. I get a function e of z, which is equal to e z plus lower order terms. So I just take the linear combination of this, of cosine and sine.
But with some powers of t, multiplied by some powers of t.
Yes, sure. Just I do everything to get the exponential here, and finally this exponential. I call this a false exponential. This is a false exponential. It behaves like an exponential for large z, but for small z, it is actually some combination of the Airy functions. The funny fact is that if I take this WKB representation and do only one thing, I replace the true exponential by the false exponential, by this false exponential, then the resulting function has no singularities, including the focal point, and gives me the asymptotics. This asymptotics is, of course, expressed via the airy function, and it is, in a sense, global. In fact,
how general is this observation?
in one dimension, it is pretty general. In dimension 1, it's pretty general, and we will see an example in dimension 2 also.
It doesn't work with other types of singularities. I mean,
yes, it does, but with other types of singularities, it is a little bit more complicated, just because here we have to find the amplitude, we have a very simple equation to solve. In a more complicated case, we will see that the equation is a little bit more complicated.
The powers of t are compensated by this Jacobian functions. Right?
Yes, the powers of t compensate these Jacobian functions, and everything cancels out, and we get, so this is just a mnemonical rule, in fact. Of course, you need that we have the proof, and we have this proof, but the mnemonical rule is just very simple. Take the WKB solution, replace the exponentials by false exponentials, and you are done. Yes, if this canonical operator originated from the solution of some equation, then they will satisfy the very same equation, modulo of h square, as usual in the theory of canonical, as you solved some equation.
I'm sorry, Malon, you have to make a break somewhere.
Yes.
Now, later,
well, we are 30 seconds away from the break.
okay.
Well, so once more, this is a very simple mnemonical rule, but it works in dimension 1 very good. And I must say that if your manifold has only one focal point, looks like that, up to infinity, then the solution is global, just global. Even though one might think that the airy function is only good if your manifold is projected onto the p axis. Now, if you have something like that, but no focal point there, your representation will work. Just because for large z, airy function gives cosines and sines, and so this is all you need.